AI can churn out charts in seconds, but can you really understand it? In this short introduction, let us learn the basics of loading a dataset in R, merging it with other datasets, and produce a visually appealing graph. This is a helpful skill in business analytics and data journalism, but also in academic research. It's time for you to take control of your data once again. Why should you trust me? I'm an assistant professor in political science. I used to teach at Oxford and at Princeton and have years of experience of teaching statistics and data visualization. So let's dive right in. Okay, so today we're covering Dplyr and basic visualization in R. So we're going to learn how to open real-world data sets, how to clean and prepare data for analysis. We're going to learn some of the basic functions behind Dplyr, an important library in R. We're going to learn how to group and summarize values. We're also going to learn how to join different data sets. And then we're going to learn the basics of Ggplot, an important library in R that's used for data visualization. Okay, so I'm going to cover some of the things that I covered previously. So we're going to open first Quarto Notebook. This is what the R interface looks like. We're going to go to New File, Quarto Document. We're going to call this Quarto Document Notebook. We're going to, this is what the Quarto document looks like when we open it. We are going to switch off the visual mode and we're going to look at source. So this is what the source file looks like. So we're going to operate directly with code. And the next step will consist of deleting all the content that's in the default notebook. So we can do this by pressing Command A or Control A in Windows. And then we're going to press delete. So the clean notebook looks like this. So no information whatsoever. We're going to now paste this preamble. So this is something that I prepared. You're going to have access to this lecture. So you simply click on this symbol here, which is going to allow you to copy all this content. Then you move on to your own data frame, to your own Quarto document, and paste it within it. This is what it should look like. Of course, you should change the author to your name and then the date that's relevant for today. It's important, as I've mentioned before, that there is no space between the first line. So there shouldn't be an empty line and then dash, dash. So the very first line should be exactly this. But if you simply copy and paste the code that I provided to you, there shouldn't be any issue. In addition, it's important to note that within YAML headers, meaning this section here, indentation matters. So, of course, once again, if you copy and paste it, there shouldn't be any issues. This should not cause any problem. But if you don't paste it, then it's really important to keep the formatting correctly. Okay, we're going to save this Quarto note. We're going to save it in our dedicated work folder. In this case, this is called example. I'm going to also call this QMD file notebook, as you can see in this image. And then I am going to try to render the Quarto document to just get a sense of what this document looks like as HTML. Okay, and here it is. After a few seconds, you'll be able to see this document in HTML. It has this boring title called Notebook, and the author, your name. Of course, hopefully you change the author to your own name and then the date to the date when you are working with this document. Okay, let us add an R chunk. Remember, you can simply do this by clicking on this green symbol. This is what is going to open up a new menu where you can select the programming language that you want the R chunk to be in. Because this is R, we are going to open an R chunk, which looks like this. Once again, notice that the R chunk has a distinctive color and distinctive symbols. So it starts off with 3 apostrophes, and it also ends with 3 apostrophes. Make sure that the R chunk opens and closes. Okay, let us add our first text. So you see here a header called introduction and a simple text just before the R chunk. This is called, so I wrote in this text, this is the introduction. Let us render this document to just get a sense of how text gets reproduced as HTML document. So this is what it looks like once we render. Okay. Just to reiterate, notice that when you have the header, it's important to have a space between the hashtag and the section name. Otherwise, the section name will not be displayed correctly. Okay. So before we do anything, let us first remove all the objects that we have in our computer's memory. If this is the first time when you open R, of course, you're not going to have any objects. But if you do have any objects, this is how you remove rm list equals ls parenthesis parenthesis, and then close the bigger parenthesis. This is what is going to remove all the objects from memory. So let us now download two data sets that I got from A World in Data, which also got this data from the UN. So this covers life expectancy and urbanization. So if you click on these two links, this is going to take you to two Dropbox CSV files, which you should download and place in your work directory. Okay, so how do we do that? As I mentioned previously, the best way to figure out where these CSV files are is to use file choose. So first of all, place them in your example folder, so in your work directory. But then just to make sure that you get the path correctly, use this file choose function. This is what my path looks like. Of course, this is different from for your computer. So this is how I load the CSV files. So I have the read.csv and then file.path, and then the file is the one that I just defined in line number 2, and then the file itself, which is written here. The same thing with urbanization data or data frame or the urbanization data. Okay, once you do this, you should be able to see this in your environment. So you have two separate data frames, one that's called life expectancy and another one that's called urbanization. Notice that you have over 20,000 observations for life expectancy and over 14,000 observations for urbanization. Notice also that the file path was saved in your environment. Okay, some quick statistical concepts. So when we collect data, we often want to first summarize it. So we want to get a better understanding of what kind of data we're working with. So measures of central tendency are types of measures that help us understand our data better by telling us what a typical or central value looks like. So typical measures of central tendency include mean, median, but also mode. So the mean, this is really the arithmetic mean, the median is really the middle value, and the mode is the most frequent value. So let us have a quick look at our data set. So the first one here is life expectancy. This is what your data set should look like once you upload it to your computer's memory. So we have countries. So in this case, this is Aruba. You have country codes, you have years, and then you have life expectancy values. So 57.2 is Aruba's life expectancy in 1950, the same life expectancy in 1951, and then 52, this increased to 58.7, and so on and so forth. Okay, so once again, this is life expectancy just for Aruba. These are all the values within Aruba. And these are all the years that are present in this data set for Aruba. This is life expectancy in Afghanistan from 1950 also until 2021, but you cannot see it in the way I display this data here. But if you look at the data frame itself, you should be able to see this data covering all the years up to 2021. And then we can calculate the summary per country. So this means we're going to have a single value for Aruba. In this case, I decided to go with the ABW three-letter code. So if we average out all the life expectancy values for Aruba from 1950 to 2021, we are going to get 70.25. The same with Afghanistan. So notice that if we take the mean, rather than having 71 values for life expectancy, we only have one. Okay, so this is precisely what I'm emphasizing here. So this is life expectancy for Aruba, and this is life expectancy for Afghanistan. The other three values which you see here cannot be seen in this data frame picture that I display here, but obviously you can see them if you scroll down on your own computer. Okay, this is how we obtain this average by country, by using this basic Dplyr function. So first of all, we are creating a new data frame that's just a copy of the old one. And then we're utilizing this interesting sign, which is called pipe sign. I'm going to explain in a second what the pipe sign does. The next step is to group the countries by code. Remember, the code is a variable that represents a three-letter code for each country. And then we calculate the mean by using this command summarize, and then the new value for what we want the value to be called, and then the mean of the old value, which is life.expectancy.birth.historical. So this sign here is called pipe operator. This is a Dplyr command which allows you to pipe an object to forward to a function. So this means that you can just run multiple functions within one single line. Although this is not technically, although this is written in 3 lines, this is technically one single operation. So we first copy the old data frame. We then group our data by country code, and then we calculate the mean by country code. Okay, in more modern versions of R, this pipe operator was replaced with this sign. So in many modern versions of R or some R scripts, you may also encounter this sign. It plays the same function. This is also a pipe. For the sake of convenience, so you might see a code that looks like this. So you're creating this new data frame, and then you're grouping life expectancy by code, and then finally you're calculating the average life expectancy. Notice that this sign is different from this sign, but in essence, they're the same thing. You could also write this in, so you can also write this instead of this. So notice what is missing, what the difference here is the presence of the library name. So why do I do this? Is because sometimes other libraries may have similar functions. So sometimes R may get confused. This is particularly the case when it comes to group by. So sometimes this could, because group by also exists in other libraries, R could get confused. So you might get unexpected results. So in order to make sure that this produces the results, I want to specify that I want the program to use the Dplyr group by function. So that is why I preferred to go with this option as opposed to this other option. Okay. Another way to also write this is to include na.rm equals true. So if you remember from the previous video, what this does, this removes the na values that might be present in your column. So sometimes if you don't do this, you might end up with na as a result. So it's always a good idea to put na.rm equals true. Okay, so this is what we obtain after we run this code. So the old data frame is this. So I marked it here. This is what it looks like if we click on the environment. So the original data frame, we can click on this table symbol, which is going to open this data frame, right? So if we run this whole code here, we're going to get this new data frame called life expectancy underscore df2. Okay, so notice the substantial difference in our number of observations. So the reason why the number of observations is different is because the original data has 20,445 observations. Remember that countries have multiple years. So if you remember from the slides earlier, Aruba could be seen 71 times. So this is from 1950 all the way to 2021. This is because there are statistical values for life expectancy starting with 1950 all the way to 2021. This is the second part of the code where we're grouping by country. So once again, we're trying to figure out what is the average life expectancy for Aruba from 1950 to 2021, and the same for Afghanistan. And then we're telling R that this is the column that we want to calculate the mean for. So the new variable will be called life expectancy mean, and it will be the average of this old variable called life dot expectancy dot at dot birth dot historical dot at the country level. So this is what the new data frame looks like that only has this new variable called life underscore x underscore mean. So these are average life expectancy per country. Okay, so I guess logistically or mechanically, we all understand what the mean variable is, but more formally, the formula for a mean is the following. X bar is equal to x1 plus x2 all the way to xn divided by n, which more efficiently can also be written as the sum of all xi values divided by n. So the mean uses all the values in a data set or in a group. This sigma symbol, it's the uppercase sigma, it's called a sigma notation. So this is a notation that indicates summation. It's important to note that the mean is not resistant to outliers. It's not resistant to extreme values. So for example, if we have a data set where one variable has the following values, 10, 11, 12, 13, 100, we're going to end up with a mean that's 29.2, which could be misleading depending on what we're interested in doing with our data. But clearly you can see that 29.2 is so much higher than 10, 11, 12, 13. And this is because we have this big value, 100. So it's important to note that the means are great when we're dealing with symmetric distributions. So in future lectures, we're going to delve into the notion of what a distribution is. But what's important to take away from this example is that one extreme value, such as 100, can have an impact of increasing the mean artificially. Okay, to calculate the mean, we simply do this. Mean, and then the new data frame, dollar sign. Remember that the dollar sign is really the symbol that allows you to access one particular column within your data frame, and then the name, the data frame itself. Given the possibility that we might have NA values within that column, we simply add comma NA.rm equals true. So that gives us the average life expectancy throughout the world, all the years from 1950 to 2021 is 61.78. This takes us to the second important measure of central tendency, which is the median. So this is the middle value in a data set ordered from smallest to largest. So a median typically splits the data set into two equal halves. So it's important to note that the median has different formulas. One, when we're dealing with an odd number of observations. So for example, if we have a situation like 137, imagine these are the values within our variable. The median will be 3. So why 3? Because this is the middle value from 1 to 7. We're dealing with even numbers, then the formula changes. So the formula for the median will be the average of the two middle values. So imagine we have 1357. The median will be 3 plus 5 divided by 2, which gives us 4. Okay. So unlike the mean, the median is not so affected by the presence of outliers. So if we look at the previous data set, 1, 3, 5, 7, 100, the median here is simply the middle value, which is 5. The mean, if you remember from the previous slide, will be 23.2. So do you see how 5 is so much closer to these 4 values compared to 23.2? So this is an important example showing how the median is not pulled by extreme values. In order to calculate the median in R, we simply take the data frame that we're in that contains that variable. We add the dollar sign, and then we add the variable from this data frame that we are interested in calculating the median for. We also add NA.rm equals true. So this is to deal with the possibility that we have NA values or not available values within our column. This is because this will estimate a number. If we have NA values and we write median without specifying NA.rm equals true, we might get NA as a result. So to avoid that, we always want to add NA.rm equals true. Okay. So we learned about the mean and the median, but what about the spread of the distribution of our variable? So it could be the case that two data sets have the same mean, but they may have different variability. So this is where measures of dispersion are important because they tell us how spread out different values are. So one first measure of dispersion is the range. So the range is fundamentally the difference between the maximum value in our data set and the minimum value. So form the second important measure of dispersion is the variance. This has this ominous looking equation. So S squared is equal to 1 divided by n minus 1 multiplied by the sum of all values from I to n. It's not really the sum of all values from I to n. So it's the sum of the differences of the values minus the mean all squared. So this is essentially the sum of squared differences from the mean. Okay, so I even wrote here, so yi, xi here is the ith value. The x bar is the population mean of the variable, and the n is the population size. Standard deviation is simply the square root of the variance. So once again, this is the variance here. And then to calculate the standard deviation, we'll simply take the square root. Okay, so if we were to apply these measures of dispersion to our data set, let us first look at the range. So to calculate the range, we simply do range, and then the data frame, $sign, and then the variable that we're interested in calculating the range for. Similar to before, I'm adding the na.rm equal. And then I just want to examine what it is that range produces. So min-max now is an object that has two values, the first one and the second. As you might suspect, the first one, so remember this way of extracting values from an object. So given that this is a vector with two objects, the way we extract the first object is by simply typing in 1 and then adding these square brackets. So if we do that, it's going to extract this number. So to further prove that this is what these indices do, let's put also the second value. So if we do min-max 2, this simply extracts the second value, which is 86. Okay, so this means that the range, if we do the calculation, so the maximum minus the minimum, this simply gives us 74.5. So this is the range in our, this is the range for the life expectancy variable within our data set, 74.5. Okay, what about the variance? To calculate the variance, we simply use this function, VAR. So VAR, the data frame, and then the value, the variable within that data frame. And then do not forget about the na.rm equals true. So that gives us this number. So if we want to calculate the standard deviation, we can also simply use this function, SD, and then the data frame, the $sign, and then the variable that we are interested in calculating the standard deviation for, and we get rid the NAs. Obviously, to just demonstrate that the standard deviation is the square root of the variance, we can simply do SQRT, so the square root of the variance, right? So notice how these numbers are exactly the same. Okay, so just to illustrate what this group by and then summarize does, this is just a simple GIF file to illustrate how group by and summarize work together within the Dplyr context. So notice that in this case, so this is, imagine that this is the code that we're dealing with. So this is a simple pipe operator, the modern one. We see that we have group by, we have category 1, and then we have summarize. So this calculates the average for X, the total for X, and also the number of observations within category 1. So notice once again that this is df is the original variable. This is what group by does, and then this is what summarize does. So once again, have a look at this yourself. This, I think, will further solidify how group by and summarize work together. Okay, so hopefully this is clear now. Let us now apply these two Dplyr functions to our data set. So we have group by code. Remember, code is the variable that is a 3-letter code for every country. And then summarize. So notice how our new variable, it's called life_x_mean. So we do the same thing for urbanization. So remember at the beginning we had two CSV files. One was life expectancy, the other one was urbanization. So we want to apply Dplyr to both of them. So this is what this second block is all about. So group by country code and then summarize. So calculate urb mean, which is simply the mean for urbanization for all the countries one by one. Okay, let us first investigate the first entries in life expectancy DF2. So what did we just do? So the first entries, once we do this, they look more or less like this. So we have this data frame called life expectancy DF 238 observations. And if we do head the new data frame, that's DF2 here, comma, n equals 3, this is going to display the first 3 entries. So notice here, once again, life expectancy underscore DF2 has 238 observations. And this is what these observations look like. Okay, let us do the same thing for urbanization. So notice how urbanization DF2 has 217 observations. This is a substantial decrease from 14,021. So if we click on this, we should be able to see the main country codes. So remember that code is really the 3-letter country code for each country. So what's interesting here is that some of them have unusual entries. So rather than having a 3-letter code, some countries have nothing. This is the case here. So we have supposedly one country that has no country code. And we also have 2 additional units, OWID underscore KOS, OWID underscore WRL. So we probably want to get rid of these strange entries. I can tell you now that the regions or the units that have no code, in fact, are already country or continent aggregates. So we want to get rid of that. Similarly, the OWID are countries that have a specific status that might be recognized by the international community. So in order to not bias the results, it's probably better to eliminate them completely from our sample. So in order to do that, we first create a vector called suggestively weird labels that contains OWID KOS, OWID WRL, and the units that have no name. So this is what our weird countries look like. Okay, the next step, we would like to investigate what are these weird countries. So I would like to draw your attention to this piece of code. So first of all, we're looking at code in, if you remember from last time, this is a piece of code that allows you to match whatever is before this symbol to a list that comes after. And then this whole expression allows you to subset based on a list of names specified earlier. So given that we just did this, we notice what our weird countries are, we can actually get rid of them. So we repeat the procedure, but the only difference now is that we negate what we did before. So notice that before there was no exclamation mark, and now we do have an exclamation mark. Just as a reminder, exclamation marks are used in order to negate something. So subset life expectancy DF, where code is not in weird labels. Okay, so if we do this, notice how we end up from 238 observations to 235 observations in the clean life expectancy. So remember here, we're dropping these units. They're exactly 3, 1, 2, and 3. So we're dropping those 3. Hence, we're shrinking from 238 to 235 observations. And our new data set is called clean life expectancy underscore DF as opposed to life expectancy underscore DF2. Okay, This is what our data looks like now. So notice that we do not have the first entry that has no code whatsoever. Now we do have ABW. So let us now repeat the same procedure for the other data set. So we still have these weird labels. I would just go with the clean urbanization DF, meaning we're just getting rid of all these weird labels. Here too, notice how our new urbanization data frame, clean underscore urbanization underscore DF, now has 215 observations as opposed to 270. Okay, so this is what our new data set looks like. Let us now join the two data sets. So remember, we cleaned our life expectancy data set, and we also cleaned our urbanization data set. What's left now, hence the name, excuse the pun, is to left join the two data sets. So why is it called the left join? It's precisely because we're merging Y, so the second data set, onto X. So this is perfectly visible in this GIF file here. So we have the first data set that has observation 1, 2, and 3. And then we have our second data set that has observation 1, 2, and 4. So 4 gets dropped, and then 1 and 2 get to be merged, left joined onto the first data set. Okay, so this is how we do that in practice. We simply use this code, left join. We have our left data set, which is called clean life expectancy DF. And then we have our right data frame, which is called clean urbanization DF. We do need to specify here what is the variable that we're using as a join variable. So in this case, this is code. Remember, this is the 3-letter code for each country. So our new merged data set will be called merged data. Okay, so look at the original files. So 235, 215, and then our merged data has 235 observations. So this corresponds to the number of observations on the left data frame, which is this clean life expectancy, clean life expectancy. All right. Our data set looks like this. So the merged data looks like this. We have all these values in life expectancy. We have these values in urb_mean. Notice here that for the country with a 3-letter code AIA, we have NA, we have a not available value for urbanization. This is likely because AIA is not a country that's in the urbanization data frame. So thus, it becomes filled with NA when we do the merge. This is how we remove the NA values from our data frame. So we simply do subset, and then we do NA dot omit merge data. So let's imagine we want to have a clean data set where none of the values is missing. So this is the simplest way to do this. So this is what allows us to see the first 10 entries. So that's precisely the purpose of this function. We might also be interested in understanding what were the countries that we dropped. So this is exactly what the point of this function is, or what this point of this command is. nrow merge data minus nrow merge data 2. So the merge data, the original one, has 235 observations. The second one, the one in which we removed the NA values, essentially the ones that had missing values for urbanization, the second data set has 214 observations. So this means that 235 minus 214 gives us 21 observations that we dropped as a result of this NA omit procedure. So notice them here too. So 235 minus 21 gives us 214 observations. Okay, what are those countries? So one important task when we do merges or when we drop data is to understand our data. What are the countries that we end up dropping? So in order to understand what the countries that we dropped are, we simply do this command. So merged data, not complete cases, merged data. Will allow us to see what are the countries that get dropped as a result. So these are the countries that have missing values for the urbanization variable. So let us have a quick look what these codes mean. So a simple way to do this is to do the life expectancy DF, the data frame, code in countries dropped code. So it seems that the countries that we ended up dropping are these ones. So the 21 that we ended up dropping are the ones that do not have urbanization data. So let's imagine that for this task, we want to have a complete data set. So we do not want any missing values, but it's important to be aware of what the countries are that we ended up dropping. So there they are. Okay, finally, we can get to data visualization. So Ggplot2 is the most important library that's very versatile and allows us to display our data in an aesthetically but also scientific way. So before we get to visualize the data, it's important to install and load the library. So one quasi confusing thing about Ggplot is that the relevant library is Ggplot2, not Ggplot. So this is a confusion that many people make, and it's normal to make this confusion. So to install it, you have to press or you have to type install.packages Ggplot2. So the same thing when we load the library, notice that we have library Ggplot2. And this is the kind of scatterplot, the very first scatterplot that we want to produce that depicts the correlation or the relationship between urbanization and life expectancy. So every single dot here is a country that has a value for urbanization and also a value for life expectancy. So just to save this graph, so within our working folder, let's imagine that I'm working in lab. Let us create a subfolder called graphs. So as I mentioned before, it's highly important to be organized and to make sure that your workspace is clean, that has graphs folder, that has data folder, and so on and so forth. But in addition, this is also relevant in order to make sure that you know where the graphs are located. So in this specific case, I have a lab folder, which is inside of week 3. And then what I want to do, I'm creating a new folder inside lab, which is called graphs. So I encourage you to also create a graphs folder within your own working directory. The next step, we're going to paste. Remember that we downloaded lifeexpectancy.csv. This is one of the Dropbox files. I would like to place it in this newly created directory called graphs. So this is more or less what this should look like. So at the very end on the right, you see the data set called lifeexpectancy.csv. Okay. In order to identify the correct path where you're going to store your pictures, your GG file, a ggplot objects, we're going to use file choose. So this is going to allow you to manually interact with R, which is going to take you straight to your work directory. So this part here is going to differ for every computer. So this is what I have on this machine right now, but this will differ for your machine. And this is the part that if you have week 3 lab and graphs, this is the one that stays the same. The final part of this path is really the file itself. So life expectancy.csv. Okay, so this is the path. So this is the reason why I'm setting this work directory, as you can tell here. So notice week 3 lab. And then I'm saving this fig1 into graphs, right? So that's the point for doing this. These other options are the height and the width, and then the DPI, so dots. So essentially, these are responsible for how square you want the picture to be, but also how detailed you want the picture to be. So the bigger the DPI, the more detailed it would be. I think for most purposes, 300 is more than enough. The one thing that I wanted to emphasize, right, so this was the relative path option. So this was this here. The other option is absolute path. So rather than you writing file dot graphs, you simply you write down the whole path, including the file itself. So if somehow you struggle with this idea of a relative path option, an absolute path is also one possibility. This section here is the same as this section here. It's up to you. Okay. Once we figure out the path, we can finally delete file choose and then the life expectancy.csv. And then finally, we can make the graph itself. So how do we make the graph? We use Ggplot. Here it is. This is the data that we're using. Then we have to have a mapping. So we have to have an X variable and a Y variable. Notice how our X is mean. This is the mean that we created. And for the urbanization, the same for life expectancy. We're then using geom point. So this is what allows us to depict these countries with dots. And then we simply create X-axis labels and Y-axis labels. So notice now that our X is called urbanization with an uppercase U and then lowercase other letters. And the same with the Y-axis, where we have life expectancy that has uppercase first letters and lowercase letters that come after that. We can obviously add a title. So here's how we do this. We simply add GG title. In this case, I couldn't be more inspired, so I provided just example title. I can also opt for a black and white background. So rather than having it gray, it might be better to have it black and white. This is how we achieve that. Theme_BW. We can also trace a line of best fit that kind of shows the clear connection between urbanization and life expectancy. So we simply do this by doing geom smooth method equals lm equal comma se for standard errors equals false. We can also be more specific about the starting point for the X and the ending point for X. So this is the point of this. We're starting from 0. Notice the use of the function SEK. Remember this SEQ. So this creates a sequence essentially from 0 to 100 in increments of 20. And then this is what this looks like. So this allows us to set limits to our data set. So notice the difference between figure 1 and figure 2. So there's fundamental, you might think that there's a substantial difference, but in fact there isn't. So the reason why this appears steeper is simply because of how restricted the X and Y axes are. So because this one starts at 30 and it ends around 90, appears much steeper than the one on the right, which starts at potentially also 40 and it ends at 100. So in the end, there's no difference between figure 2 and figure 3. The only difference is how constrained the axes are. Okay, we might be interested in labeling the data. So we might be interested in actually labeling those points that we have in the graph. So this is the first thing that we do. We're extracting first the variables that capture the country name. So these are entity. So this is literally the variable that tells us, okay, this is United States of America. This is Aruba. And code, this is the 3-letter country code. So first, we want to make sure that our code, the 3-letter code, is not duplicated. And then we would like to merge these values to merge data to by code. So we take the 3-letter code in both data frames, so 1 and 2, and then we want to create a final data frame that's called merged data 3 that contains all the values in merged data 2, but also now the country label, essentially entity. Okay, so this is how we add entity to our graph. So we want, once again, we want to label all the points in that ggplot. We want to know what countries we're dealing with. So here's the final result, right? So notice how all these points now have a label associated with them. Okay, so what if we want to use selective labeling? What if we want to just select certain countries and just label certain countries? Let's imagine that we want to label the US and Italy. How do we do that? We already know how to do that, right? So we create a vector that has these two values, Italy and the United States. And then we're simply doing a subset. We're simply subsetting the data, merge data 3, and we say entity in countries of interest. So where countries of interest is this vector here. So this is going to create a new data frame with 2 observations, Italy and the US, which we can add to here. So this is going to give us, the, so notice, apologies, the data is here, Italy, USDF. So this is this data frame that we just created. So this is going to label only 2 countries, these 2. Okay? So I hope this is helpful. Like this makes sense. Okay, finally, maybe another better way to display this in a more aesthetically pleasing way is to use geom label. So notice the difference here between geom label and geom text. So when we use geom text, this is the output. When we use geom label, this is the output, right? So we see that the labels are much more vivid and much more visible. So it's really, it depends. It's you have to decide on your own what makes more sense, or does it make more sense to use labels? Where does it make more sense to use text? Okay, but then which country is the US and which country is Italy? Because here in the end, is it this one? Is it this one? Probably is this one, but how do we know? The way to know is to use the geom label repel. So in order to use this function, we need to first install a new library. It's called ggRepel. So as the name suggests, this is going to allow us to trace where these labels come from. So it's going to tell us specifically that the US is this dot here and Italy is this dot here. So this is much more precise, and it prevents us from engaging into a guessing game. So this tells us much more quickly which point is what country. Okay, we have covered quite a lot of ground, including the basics of Dplyr. So summarize and calculating the mean for data, but also how to clean data before we use Dplyr. We have also looked at the left join function. And then we learned how to use Ggplot, one of the most versatile libraries in R that allows us to produce aesthetically pleasing figures. We also learned how to customize labels, how to use titles, themes, and how to how changing our axes can have substantial implications for what our data looks like in a graph. Thank you and see you in the next video. I hope you enjoyed this video. If you found it helpful, please give it a like and press subscribe. Also, if you have any questions or comments, feel free to leave a comment down below. Thank you and see you in the next video.